Thank you for the great talk, and I would like to thank again the three speakers and for their great presentation and their work. And this concludes our session. Thank you very much for coming here. And if you want one takeaway from this session, make sure to sign your Git commits.
Hello. Oh, thank you. Do we have any of the authors for this session? Yeah, please come and see me. sure. I'll ask them to put the slides. So you control the slides with this. Yeah, sorry. You control the slides with the. I think it's this. Yeah. Okay. Okay. Good. Can we have the slides for the first presentation, please? Okay, I guess we're ready to start. Good morning, everybody. My name is Ashraf Matrawi. I'm from Carleton University in Canada, and we are about to start our session on machine unlearning. We have 3 papers, and we're going to start with the first paper on trash deleter presented by Ching Gong from the University of Virginia.
Hello. Okay. Hello, everyone. I'm Chen Gong, come from University of Virginia, and today I want to introduce a new concept on learning in offline reinforcement learning. Actually, there's so many interesting applications for offline reinforcement learning, like the large language model. It can use the RLHF algorithm to train the agent. But in here, this traditional offline reinforcement learning, this agent is different from the large language model. And in here, we hope to train an agent, use a fixed data set here. And this data set is in this form, the trajectories. Trajectories consist of the state, action, and the reward pairs is sequence. And here it means that in this state, if we do these actions, and we will receive a reward from the environment, and then the environment will transit to another section. Yeah. Why we need to promote the unlearning in trajectories? For example, there are three scenarios. The first one is automatic treatment plans. And in here, we will record some patient-sensitive information. And the second one is vacuum robotics, and sometimes this robotics will remember the sensitive information for a room. The last one is a law requirement. For GDPR, it means that users have the right to delete the data and erase its impact on the agent. So, for the privacy concerns and the law requirement, this motivates us to develop offline reinforcement on learning. The most straightforward solution is retrain. It's pretty easy and can be a golden line for our algorithm. Actually, it's a reference in our experiments. We can directly drop the unlearning dataset and retrain the original dataset from scratch, right? It's pretty easy, but this is time-consuming and expensive. And sometimes unlearning requests can be made frequently. So how can we develop efficient unlearning method to approximate this process is pretty important. The next solution is fine-tuning. It's also pretty easy and very popular in other fields of dataset unlearning. We can directly drop the unlearning dataset and fine-tune the agent on the remaining dataset. But we know that this process is unreliable, right? The third one is random reward. We know that agent learn from the reward. So if we put the reward random, maybe for the same actions and the state pair, the agent will be confused. Maybe in here is this reward, in here is another reward. And the agent will think, oh, it's a one actions, it's a one information, and it will ignore it during the training process. But we know that if we make the reward random, can make the training is very unstable. It's a joke here. Stable and highly efficient forgetting is what we needed in our paper. So we propose the trajectory deleter. In here, I will introduce why the reinforcement learning training is unstable. Actually, we have two functions to train. The first one is a value function. It means that in one state, if we do this action, how many cumulative reward we will receive when the agent be the turbulent state. The next one is the agent. It's a policies. It's input a state and output actions to tell the agent, oh, you should select these actions. And if we train these two functions simultaneously like GAN, this process is pretty unstable. And then I will introduce the objective functions of the offline reinforcement learning. It's a high level introduced. We can put the agent and the value function training together. It means that in each state, we hope the agent to select the optimal actions to make the value function maximize. Intuitive brought the idea from the gradient set from other area. Learn is maximizing, so unlearn is minimizing. And to keep this way stable, so we should learn on the remain data set, but unlearn on the trajectory data, the trajectory target trajectories is unlearn trajectories simultaneously to keep this way more stable. But a better news is that if we directly use this forgetting training process, it's unstable because we cannot provide a convergence guarantee for the agent. So we introduce the second convergence training. In this convergence training, we hope the unlearned agent to learn the value functions of the original agent on the remaining data set. Why we should do this? Because we have a theory here built from the previous works. It told us we will do this process. The convergence training can make the unlearned agents converge to the unical optimal function or agent. But it is noticed that here, we should do them separately. We should do the forget training first, and then we do the convergence training. We cannot do them simultaneously. So another question is that if I am users, others told me that I have deleted your target data. How can I trust the thing? How to determine whether the trajectory deleted is unlearning successful? So this is the second part of our paper. We can use the membership inference attack as an auditor like the previous works. Is that we have many shadow agents, and we can ensure that the shadow agent include the unlearning trajectories. But we don't know the unlearning agent is include the unlearning trajectories or not. So we can compare the features between the shadow agents and the unlearning agents to do the decisions. I mentioned before, this stability is a drawback in offline area training. But a good news here, it can be a tool to improve the auditor's efficiency. How to do that? We can use the unstability of the offline reinforcement training and directly train the original agent on the original data set to do some fine-tuning, and then we can obtain multiple shadow agents. And we believe these shadow models will be different. But for not supervised learning, we cannot do this because the training of supervised learning is pretty stable. And then we can extract the features of the unlearning agent in these features, and then extract the features of the shadow agent and compare the similarity between the features. Yeah, there's so many details here, and I don't want to go in detail then. Maybe you can research a paper for details. Yeah. The final section I will introduce our experimental design. The first one is effectiveness of the auditor. The next one is effective of the trajectory deleter. The third one is the impact of the hyperparameters. And this is our investigated algorithms. And I selected 6 SOTA offline RL algorithms to train the agent. And we use the precision and recall to measure the accuracy of the unlearning rate. And the last matrix is average returns to measure the performance of agent. Yeah, before I introduce the main result, I would say it must our result will be good. Otherwise, this paper will be rejected, right? So I just want to introduce some key insights from our experimental result. Here we have 2 outliers here. We can say in half the chair, the unlearning rate is pretty low, but for Hopper and work 2D, the average unlearning rate is high. This is why, because we find the tracked auditor may have the difficulty with algorithm when the training is unstable, like these curves. It's pretty unstable. In the worst case, in Hooper and work 2D, the unlearning rates use this algorithm is pretty high, so it's a limitation of our paper, and it's also an interesting future works. I think to develop a more exact trajectory auditor method is the base of the trajectory unlearning, and we should explore more in the future works. The next keynote is that we only used 2.2% time compared to retrain and achieve the similar result compared to retrain. And retrain is a reference, is our golden line. And these tables told us the importance of the convergence training. Without convergence training, we can see here, the remain data rate have a increase. It means that we do the forget training, it will also forget some trajectory in the remain data set. And then, without the convergence training, the return means the performance of the agent will have a big decreases. So the convergence training is pretty important in our algorithm. It also highlights that the second point is that in offline reinforcement learning, the convergence problem is always we should pay attention to develop a more stable convergence training is pretty important. The last one, I want to introduce the hyperparameters to say how to balance the forget training and the convergence training here. In this picture, I make the forgetting step and plus the convergence step equals to 10,000. 10,000 is only 1% of the training step for retraining. With this picture here, the forgetting step can significantly impact the unlearning performance, like these curves, the yellow curves. But for the blue bar, we see that the convergence doesn't sensitive to the agent's performance. So sometimes a small value of convergence step is good, and the forgetting step can be large. And in our paper, we set the convergence step is 2,000, but the forgetting step is 8,000 in our paper. Overall, this paper proposed a trajectory forgetting method in offline reinforcement learning, and we hope this paper can bring some ideas for the future large language model training. We know that the large language model using the RLHF and can be seen as the specific types of the offline reinforcement learning. So I believe our paper can bring the insight for this area. And thanks for listening. This is all my presentation.
Thank you very much. We have time for a couple of questions.
Hi.
Hello. Thank you for your presentation. In your experiment that you showed how to unlearn the cheetah, okay? But do you need a shadow agent for each user that wants to be forgotten?
Sure. I think yeah, it's true. So sometimes you mentioned the training of the shadow model is no inefficient, but in our method we put this way, we can simply to fine tune the models on the remain data on the original data set, and we think this process can improve the efficiency of the shadow model training.
So you will need a new agent for each new user that wants to be forgotten, or can you like merge some user together?
Yeah,
Sure,
sure, together. Yeah, compare them together.
Okay. Thank you.
Any other questions? Yeah, let's thank the speaker one more time. Thank you very much.
Thank you.
Second paper, please. So on the second paper, we're going to learn about reinforcement and learning by De Jong Yi from the University of Technology, Sydney.
Hi, good morning, everyone. My name is Da Yong from the University of Technology, Sydney. So today I'm very happy to share our recent research here. And our research is about reinforcement on learning, which combines the reinforcement learning and machine on learning. So machine on learning is a process of selectively removing some specific set of data from a well-trained machine learning model, and it can ensure that the model will behave as if these unlearned data has never been used in the training process. And reinforcement learning is another set of is another type of machine learning where an agent learns to make the decisions by interacting with an environment to maximize its cumulative rewards. So specifically, the agent will observe some states from the environment, and then it will take some actions against that environment. And then the environment will send some feedback in the form of rewards to the agent. And based on the rewards, the agent will adjust its behavior to refine its decision-making strategy. Now, when the machine on learning meets reinforcement learning, it creates a new concept. We call this reinforcement on learning. So reinforcement on learning enables an agent to forget its training environments, including all the previous learned behavior and experience and all the knowledge. So the result is the agent will behave as if it enters this environment for the first time. So the motivation of this work includes three aspects. First, it aligns with the policy regulations such as GDPR to enable the users to request their data to be removed from the agent. And then the second one is that it can it enables the agent to remove the incorrect and outdated information from the model. And finally, it adapted agent to any changes that some learned information has become irrelevant or the sensitive. So now we define the problem. So first we define the learning environment as a tuple M, which includes 4 components: a set of states, a set of actions, a transition function, and a reward function. And we also define a set of learning environments from M1 to Mn. And we also denote the target on learning environment as Mu. So the problem is, given a learned policy pi, how can we update the pi to pi prime such that the cumulated rewards received in the learning environment is minimized, but the rewards received in the other environments remain the same? So so basically, the aim is to forget this unlearned environment, but maintain the agent's learned behavior in other environments. To address that problem, we propose 2 methods. The first one is a decremental RL-based approach. It includes 2 steps. So first, the agent will thoroughly explore the unlearned environment to collect a sufficient number of experience samples. And then in the second step, the agent will be fine-tuned in the unlearned environment using the collected experience samples with the proposed loss function. So this loss function, in this loss function, the first term guides the new policy pi prime to work efficiently in the unlearned environment. And then the second term encourages the new policy pi prime to have the same performance as existing policy in the remaining environments. So this approach tries to gradually erase the agent's learned knowledge in the unlearned environment. And the second method is a poisoning-based approach. It includes 3 steps. First, it applies a random poisoning strategy to modify the transition function of the unlearned environment, and then the agent learns in this modified environment to learn new policy. And based on the agent's learned new policy, we update the poisoning strategy and then repoison the unlearned environment. So this approach encourages agents to learn some new but incorrect knowledge to forget this unlearned environment. We give more technical details for the second method. So first, we modify the transition function TU by using poisoned transition function TU hat. This means that when the agent takes some action A in state S, the agent will observe a new state S hat prime instead of S prime, and then we retrain this agent in this modified environment using the poisoned transition function. And then based on the learned policy, we update the poisoning strategy, use the proposed reward function. So this reward function first quantifies the difference between the learned policy and the existing policy. And then it combines the rewards received by the agent in the remaining environments when using the current policy pi I. We now compare the 2 approaches. So the first approach, the decremental RL-based approach, it directly adjusts the agent's policy, and then it basically relies on fine-tuning the agent's policy without modifying the environmental dynamics. By comparison, the second approach, the poisoning-based approach, it directly modifies the unlearned environment. So it's more computationally intensive than the a decremental RL-based approach because it includes an iterative process of adjusting the poisoning strategy to modify the unlearned environments. But at the same time, the poisoning-based approach is usually more effective than the decremental RL-based approach because it directly targets at the environment's underlying structure to ensure a thorough unlearning process. To evaluate the 2 methods, we use the 3 platforms. The first one is the Grid Vault, and the second one is the Virtual Home, and last one is the Maze Explorer. And we also propose 2 baselines. So the first one is learning from scratch. So this is akin to the general machine learning. So for this method, the agent will be retrained in the remaining environments. And the second baseline is the non-transfer learning from scratch. So this method retrains the agent in all the environments, including the unlearned environment. But when we retrain the agent in the unlearned environment, we will use an inverse loss function to minimize the agent's cumulative rewards. This is the general results. So we can observe that after unlearning, the agent's performance in the unlearned environments reduces when using both proposed unlearning methods, which is evidenced by more steps to complete the tasks and fewer received rewards. This is another set of general results. So when taking a closer look at the first pair of bars in each figure, we can see that before unlearning, the agent receives high rewards and uses few steps to complete their tasks. Then after unlearning, the agent performance declines significantly with increased steps and reduced rewards. So this means that the proposed methods focus only on the unlearned environments without compromising the agent's learned behavior in the other environments. Now the adaptability study. So the left figures include the results of the proposed 2 methods in different environment sizes. So we can see that with the increase of the environment size, the difference in both steps and rewards is magnified for both methods because the because a larger environment size will introduce additional states for the agent to navigate, and this will make the learning task more complex, as the agent has to modify its policy to adapt to the enlarged environment. And the right figure indicate the learning results of the two methods with different environment complexity. So here the complexity is represented by the number of obstacles within an environment. And we can see that the learning results of the two methods remain very stable because both methods focus on the policy adjustments according to the transition function instead of the number of obstacles within an environment. Now the computation overhead. So in this table, we can observe that both proposed methods are much more computationally efficient than the baselines due to their less exhaustive exploration of the environments. And the last one is the privacy study. So this study is conducted by using the recommendation systems. So in this table, we can observe that before unlearning, the recommendation policy for the unlearned user can be as high as 92%, but after unlearning, the accuracy are significantly reduced to around 68% and 64% for both for the two methods respectively. And at the same time, we can see that for the remaining users, their accuracy and rewards remain almost unchanged. So this indicates the efficacy of the proposed methods. Finally, the conclusion. So in this paper, we propose a new concept, reinforcement learning, which can be used to protect the model owner's privacy and the environment owner's privacy. And to address this, we propose two learning methods, which are decremental RL-based and poisoning-based approaches. And we conduct extensive experiments to evaluate their effectiveness. And the results indicate that both methods can successfully degrade agent ability in the unlearned environment, but preserve its learned behavior in other environments. Yeah, that's all from me. Any questions?
Hi, I actually have two questions. So the first question is, why do you formulate the in reinforcement learning, reinforcement unlearning problem as a minimization problem? Because if I want to unlearn my experience from a certain environment, MU, it does not mean that I want to minimize my performance there. Just I forget that I have learned there, not necessarily to perform badly in that environment. So that's my first question. My second question is, in your poisoning-based strategy, why did you change the next state in the transition function instead of poisoning the reward?
So for the first question, I use an like a motivating example. So, for example, I'm quite familiar with here, so I can easily find like everything here. For example, in this city, I can easily find like any landmarks here. So basically, if I forget this city, so I'm usually hard to find them. So it's different from the like traditional machine learning. So based on the paper, we defined it. We perform like deterioratively in the unlearning environment.
Okay, thank you.
Okay, for the second question, I haven't tried poisoning the reward function. So our basic idea is to change the unlearned environment and to enable the agent to learn new but incorrect information. So the straightforward is to we add some fake obstacles like in a greater world. So the agent still learns the information, but that information is not correct.
Okay, misleading.
And still in order to to reduce the agent performance.
Okay, thank you.
We have time for one quick question. If anybody has one. Okay, let's thank the speaker one more time. Thank you. Third presentation. So the third presentation is on provably unlearnable data examples by Dirwei Wang from Cicero's Data 61. Please.
Thank you, everyone. My name is Dirwei Wang, and I'm going to present our paper, Provably Unlearnable Data Examples. The authors of this paper come from CSIRO's Data 61 and the University of Chicago. Also, the project is funded and supported by Cybersecurity Cooperative Research Center of Australia. In this talk, I will first cover the background and motivation of our work. And next, I will introduce the proposed theory on the certified learnability of data. Also, I will go through some major experiment results. And at the end of this talk, I will introduce some immediate applications of our work and also directions for further improvements. As many of you are aware, the learnability of public data can actually pose some great risks. In early days, attacker can collect data from public domain and train shadow classifiers for membership inference. Also, this data can be used to train substitute models for launching transferable adversarial attacks against other black box models. Nowadays, with advances in foundation model, especially open large language models and open large vision models, and also PEFT techniques, data exploitation has never been easier. The attacker now can collect less data, but do more harm. So for example, the attacker can collect data from social media and use them to fine-tune pre-trained models and make these models as adversarial domain experts, which can expose sensitive knowledge. In a recent MIT technology review, an artist has his paintings being used in the fine-tuning of a stable diffusion model, and this stable diffusion model will later generate images mimicking the style of the paintings, and the fine-tuning only requires 20 paintings, and obviously this damages the intellectual property of this artist. There are several laws and regulations from different nations trying to stop this action. However, unfortunately, there is no strict guarantee on the learnability of data. And to reduce the learnability of data, there has been a line of work named Unlearnable Examples. Also, we have other names for this line of work. So in these words, data points are perturbed to unlearnable examples before publication, and machine learning models trained on these unlearnable examples will demonstrate quite poor performance on clean data, which means they have a very low utility for the data from the same domain. However, there are several problems for the current research of unlearnable examples. So the first is the generalization issues caused by different and diverse pirate models and training strategies in the wild. Second, evaluating unlearnable examples is quite hard due to the stochasticity in the training process. Also, in this paper, we discover a new threat named recovery attack. And in this attack, the attacker can slightly perturb the weights of a pirate model trained on unlearnable examples. And then with a small portion of clean data and projected SGD, the performance of this model on clean data can be restored to a near normal level. And this attack might be particularly interested by attackers in federated learning setting because the attacker can upload a local client model which was attacked to poison the global model, so the global model will violate certain data privacy or data availability protocols. So all these problems suggest that unlearnable examples are very vulnerable at the moment. Motivated by these problems, we want to ask this question in our paper. Given a set of unlearnable examples, can we establish an upper bound on the utility of part models trained on them? Obviously, this question is very hard to be thoroughly answered. And obviously, training with different models and learning algorithms for millions of times to estimate this upper bound is not practical, right? And also, there is no tool for computing this upper bound at the moment. But in this paper, we find that it is possible to derive such an upper bound with some constraint. So to this end, we introduce our proposed frameworks on the certified data learnability. There are 3 parts. In the first part, given a dataset DS to be protected, we will search for a set of perturbation delta under the help of a surrogate model. So after applying this delta to the dataset, it will minimize the training loss of the surrogate. Also, for this surrogate, we use random weight perturbation to make it more suitable for the later certification process, and also let us generate more robust, provably unlearnable examples, or PUE. In the second part, given the previously trained surrogate, we will randomize its weight using Gaussian noise. And for n times, for each randomized copy, we will evaluate its utility using some matrix A and a test dataset. So this matrix A can be any matrix, so that means our framework is quite generic and can be applied to different tasks and data modalities. Later, given all the results, we will compute a Q-eta learnability with the help of a quantile parametric smoothing function. We also display the definition of Q-eta learnability here. So the green highlighted part is the guarantee on the maximally attainable utility of part models. And also we have some constraint. So here we have a certified parameter set. As long as the trained part models with their parameters falling within this set, this guarantee will be true. Later in the third stage, if the defender has no access to this private test dataset, the defender can also sample a test set from a closed domain and use that to compute a generalization learnability score with the help of Hofstad's bound. To the best of our knowledge, this is the first certification framework towards the effectiveness and robustness of unlearnable examples. And how to certify it? So first, we will have a quantile parametric smoothing function, or QPS function, and this function takes the randomized parameter or weights of the model as input and computes the model utility at a given quantile Q among all attainable model utilities, which is the population. And also, we will have a perturbation bound on this QPS function. And this bound helps us to certify the learnability and calculate a certified parameter set, which scales with eta. We also have our certification algorithms here. Due to time limit, please check our paper for more details about the algorithms and theorem proofs. So examined some key properties of the certification. Based on certification results on different datasets, we find that using larger values of Q and eta in the certification can help us to certify higher learnability scores. Also, we introduce random weight perturbation for training better certification surrogates. By comparing the certification results from RWP surrogates and the baseline, we find that the RWP surrogate can produce higher certified learnability on the same set of unlearnable examples compared to the baseline. This means RWP can help us to create better certification surrogates. Based on the RWP surrogate, we also generate something called provably unlearnable examples. We compare PUE with the baseline, and we find that under the same training method, which is RWP, PUEs have lower certified learnability compared to the baseline. This means that PUEs can lead to more robust protection against certifiable adversaries. Beyond this, we also evaluated the protection power of PUEs against pirate classifiers beyond the certified parameter set. We evaluate the protection power using recovery attacks and compare PUE with another two baselines, namely EMN and OPS. We find that it is actually harder to recover models trained on PUEs than recovering models trained on the baselines. This means that PUEs can also provide more robust protection against those general adversaries outside of the certifiable parameter set. So, at the end of this talk, there are some immediate applications of our work. First, certified learnability can serve as an evaluation metric for unlearnable examples. Second, certified learnability provides a data availability guarantee before publishing the data to a public platform. Also, based on our work, we can generate robust provably unlearnable examples for better protection of the data. As for the directions for improvements, first on coverage, we can expand the certified parameter set by improving the certification algorithm. This allows us to capture more pirate models in the wild. On tightness, we can certify higher learnability by training better surrogates. And at last, on the efficiency, we can accelerate the PUE generation and surrogate training process. Thank you for your attention. Please let me know if you have any questions.
Do you have any questions from the... Okay, I'll go ahead.
Well, congratulate again on your distinguished paper award, and really nice work. So I wonder if the surrogate model, the learnability of the sample will depend on the model structure or the set of other training samples, like they may be correlated. So how do you address that part?
Thank you for the question. Yes, actually, we have a set of experiments in our paper testing the impact from model architectures. And we find that generally, for the transferability of the protection, it is it can transfer between different model architectures. If we generate the perturbation based on, let's say, ResNet 18, the perturbation can still be useful for other architectures like ResNet 50 or DenseNet. And in the certification, of course, if the surrogate model gets larger, it will bring more challenges to the certification because we need more time for the process, and also we may need to have some limitations like curse of dimensionality. Yeah. Thank you.
Okay, thank you.
Thank you.
Any other questions from the audience? Okay, let's thank the speaker one more time. Thank you.
Thank you.
This concludes the session, and enjoy the afternoon.